So, welcome everyone to this session of the Gamma seminar. Our speaker tonight is Asier López-Gordón and will give us an introduction on integrable systems. So, whenever you want, Asier.
Okay, thank you very much, Xavi, and also Javi for organizing this seminar and for giving me the opportunity to give this talk. Okay, so today I will give an outline of the basic ideas about integrable systems and especially about the so-called Liouville integrability and Arnold Liouville theorem. This is a really broad topic, so there are many things that I will not cover and many things that I do not know, but well, I will give just the basic ideas, let's say, in the easy cases. Okay, so I will first give an introduction to the topic, then I will introduce the notion of Liouville integrability and present the Liouville-Arnold theorem in its, as I said, its easier formulation with easy assumptions, how to obtain action angle coordinates. Then I will talk about the Hamilton-Jacobi equation and how this can be used for obtaining action angle coordinates. After that, I will talk very briefly about Kolmogorov-Arnold Moser theory. And finally, I will sketch some generalizations of these results that can be done in other contexts. Okay, so first of all, what is an integrable system? Well, roughly speaking, if we have a mechanical system with n degrees of freedom, then we know, then we call it a completely integrable system if it has an independent and compatible in a certain way constant of the motion, where n is the number of degrees of freedom. And these types of systems are called this way because they can be completely integrated, obviously. And by that, I mean that its equations of motion can be reduced to quadratures. Okay, so more precisely,
Sorry, could you explain what that means, that the solution can be reduced to quadratures? Because maybe no.
Yeah, well, quadrature is essentially an old term synonym for integral. So basically, this is used when you have a differential equation and you can reduce find its solution in the sense that you know the solution of the differential equation is given by a function or a set of functions defined by integrals. I don't know if that's
yeah, that's definition. I was only asking for giving it. And also it can be interesting to say that there are several definitions of integrable system.
Yeah, of course. Yeah, you are completely right. Okay, so well, as as it had been introduced in the previous sessions of this seminar, I assume that everybody already knows what a symplectic manifold is, but well, and the notion of Poisson bracket and so on. But let me recall that if we have a a symplectic manifold, then we can define its Poisson bracket, which is Lie bracket on the algebra of functions, of differentiable functions, on this way, where xf denotes the Hamiltonian vector field associated with the function f. And we will say that a collection of functions on a symplectic manifold, or more generally on a Poisson manifold, are in involution if the Poisson bracket of each pair of function vanishes. Okay, let us consider a Hamiltonian system M omega h, then we will say that a function is we have that a function is a conserved quantity if and only if it's in involution with the Hamiltonian function. I think I'm not sure if Xavi already mentioned this result in his talk, but well, I think it's worth reminding. Okay, an additional concept that this one I think it was not introduced in the previous talks is the one of Lagrangian submanifold. So if we have a symplectic manifold, a Lagrangian submanifold is an submanifold of dimension half the dimension of the symplectic manifold, and such that the symplectic form vanishes on it. Well, there are other related notions of isotropic and quaisotropic submanifolds, but since I don't need them, I will not cover them now.
May I have a comment?
Yeah, of course.
Yes, there is a fun, so it is also true that it is a famous motto by one of the most important researchers.
Yeah, I should have told you that everything is a
Lagrangian manifold. Yeah, everything that is important in physics, everything that turns out to have a role in problems in mathematical physics, at the very end, in some way, it's a Lagrangian submanifold.
Yeah. I should have put that, wrote that quote by Weinstein.
Yeah.
Okay, thank you. Well, for instance, one of the many things among everything that is a Lagrangian submanifold, I have wrote this proposition as an example. So consider the cotangent bundle T star Q of a manifold Q, and let theta denotes its tautological one form. I don't know if you call it tautological one form or canonical one form, well, whatever. Then we have this result that a one form on Q, be careful because this is on Q, not on T star Q, is closed if and only if its image is a Lagrangian submanifold of the cotangent bundle. Well, proving this is essentially trivial if you remember that the tautological form satisfies the following property. Sorry. Yeah. Sorry, we have this property. So, and we have that the pullback and the exterior differential commute. So, if we take the exterior differential of this expression, we have this. But as I said, this pullback and this exterior derivative commutes, let's say, so we can also write this way, and this is our symplectic form omega or minus omega, depending on the criteria of signs that you use. So yeah, basically we are saying, and this thing of here, of the left, is you can also write it as omega restricted to the image of alpha. So, well, this proposition follows from there. Basically, you only have to use the definition of tautological one form. Okay. So I will finally introduce the definition of integrable system. We will call a Hamiltonian system completely integrable, also known as Liouville integrable, if there exist n functions where n is half of the dimension of the symplectic manifold, such that they are in involution with themselves, between themselves, and also with the Hamiltonian functions, and they are functionally independent. That is, that their differentials with the Watts product is non-zero, or what is the same, that they are their differentials are linearly independent almost everywhere. These functions will be called integrals. Well, as Javi already said, there are many different definitions of integrable systems. Some are equivalent to this one, some are more general, or whatever. Well, For instance, here I have I took this definition, I think, from the book by Fomenko. But well, for instance, this thing that the integrals commute also with the Hamiltonian function, I find it a little bit redundant, as we will see when I explain a little bit more Liouville-Arnold theorem, but whatever. Okay, so this is the main result, or one of the main results in the theory of integral systems, called the Liouville-Arnold theorem. Let me first talk a little bit about the history of this theorem. Liouville in the 19th century, he wrote a paper in which he obtained like what will be the fourth statement of the theorem I have written here. Well, not even the fourth statement, like the expression for the equations of motion, but he did this just for Rn, and his proof was completely analytical and in local coordinates. And then Vladimir Arnold, in his famous book, Mathematical Methods of Classical Mechanics, he proved a more general version of the theorem using symplectic geometry, and he called it the Liouville theorem. And well, now people call it Liouville-Arnold theorem or Arnold-Liouville theorem. There are different criteria when you name a theorem by two authors, which one you should put first, if by alphabetical order or by chronological order. Well, I think when I was preparing the talk, I looked in Google and there were a little bit more results calling it this way, so I will call it Liouville-Arnold theorem. Okay, whatever. So let me finally explain this theorem. We have a completely integrable system, m omega h, and we consider a regular level sets of the integrals. That is, we have a subset of the manifold in which we fix the values of the integral functions. And well, the regularity essentially will mean this that the differentials will be that we will consider points in which the differentials of the integrals are linearly independent. Then we can say several things. First of all, that m lambda is a Lagrangian submanifold of m omega. Moreover, this submanifold is invariant with respect to the flow of the Hamiltonian vector fields of the Hamiltonian function and the integral functions. Additionally, any compact connected component of m lambda is diffeomorphic to an n-dimensional torus Tn. And finally, with what is maybe more interesting regarding applications, we have coordinates on a neighborhood of m lambda called action angle coordinates, phi si, such that, first of all, they are Darboux coordinates, so the symplectic form can be written on this way. The action coordinates si depend only on the integrals. Yeah, they are functions of the integrals. And what is more interesting is that the integral curves of the Hamiltonian vector field of the Hamiltonian functions, that is the Hamilton's equations, the equations of motion, however you want to say it, takes this expression. So action coordinates are conserved quantities, and angle coordinates, their time derivatives are functions that depends exclusively on action coordinates. And these functions, omega I, are called frequencies for obvious reasons. Okay, so now I will sketch the proof of this theorem. I will cover the proof with some detail, but there are certain technical aspects that I have omitted. If someone is interested, I can provide you several references. Okay, so first, let me prove items 1 and 2. This was that the M lambda is a Lagrangian submanifold and invariant under the Hamiltonian flow. These ones are easy, more or less, the easy steps. Okay, so first of all, we have that since we are assuming that our integrals a Poisson commute, so they are an involution, we can rewrite this on this way, that the Hamiltonian vector field of its Fj acting on Fi vanishes. But we can write the tangent space of M lambda as the kernel of the differential of these functions, because this M lambda is just defined as a level set of Fi. And hence, these vector fields are tangent to M lambda. Or what is the same, their flows leave M lambda invariant. So we have proven the second statement. Okay, in addition, we know that we are assuming that these Fi, these differentials are linearly independent. But since the symplectic form defines an isomorphism between one forms and vector fields, then the Hamiltonian vector fields are also linearly independent. So we have n vector fields which are tangent, which belong to an n-dimensional tangent space, and they are independent, so they form a basis of this tangent space. And finally, using that, we can write the Poisson bracket on this way, well, by definition, and it vanishes since we have that omega contracted with its pair of vector fields of the basis of Tx lambda vanishes, then it must vanish for every pair of vector fields on this tangent space, and hence it is a Lagrangian submanifold. Well, and I haven't said that it's well, the dimension of M lambda. I think I have not said this, but it's quite obvious by definition. But just in case, the dimension of M lambda is n, because it's well, you are imposing n constraints on a 2n dimensional manifold if you want. Okay. Any questions so far? Comments? Okay.
Comments, the must always be.
Yeah.
I mean, there is one comment I can do, is that when you have the n integrals of manifolds in involution, yeah.
Uh-huh.
In the Darboux theorem, you said that the omega at the very end, it can be written like the stereo product of basically the integrals of motion and other constants and other functions, yeah.
Uh-huh.
This, if you can notice that means that the Si and the Phi among themselves, the Phi with Phi and Si with Si, they are all in involution. I mean, this form of the omega tells you that you have two families of n functions in involutions, Phi I and Si. They are by themselves in involution.
Yeah, it's a good point. Yeah, you're completely
I mean, because it's very useful for other things. And what it's saying is that the Phi equal to constant, they give you a formulation by Lagrangian submanifolds. The Si equal to constant, all of them, they give you another solution in terms of Lagrangian submanifold. And this guy is telling you that locally, what you have is that you have two families of solutions, okay, that they are complementary. There is another thing is that in symplectic geometry, the variables Phi I, Si, which allow you to write the symplectic form in the way you wrote, they are called Darboux coordinates, yeah? So.
Sorry, I think I lost my connection, or you lost yours.
Hello, do you hear me?
I hear you fine, Javier.
Okay, so the thing is that to look for Darboux coordinates, you can use the Liouville Arnold theorem, because F1, Fn are when they are in involution and functionally independent, it means that there are another n functions that will be in involution that allow you to write the omega in that way. So the Liouville theorem is a way of constructing omega in the form of the canonical form by means of your integral of Moser. So, you know, there are lots of things you can say about the Liouville-Arnold theorems.
Yeah, of course.
Okay.
Yeah. In fact, I had to like decide what the main things to say about the theorem for be able to write it in a single slide.
Yeah, just one comment. In a paper with study, one of the theorems they gave me once in an preprint, it was a finished work, it could be significantly simplified by means of this theorem. I mean, it appears everywhere. Okay?
Yeah.
Really
What was this paper about? Sorry.
Darboux coordinates.
Okay. Yeah, we can discuss this. Yeah, it's interesting.
When you want.
Okay, I think I was in the proof of statement 3, which is the diffeomorphism with the torus. Okay, so basically, well, we have this more general lemma, which will be the one that I will prove or sketch the proof. That is when we have manifold, which I have called N, for it not to confuse with the symplectic manifold, of a dimension n, and we have n vector fields tangent to it, which are linearly independent and complete. Complete means that their flows are defined for any number, any real number, basically. Their integral curves. So if these vector fields are pairwise commutative, so basically the Lie bracket of each pair of these vector fields vanishes, then N is diffeomorphic to a torus times real lines, where K, the dimension of the torus, is less or equal than the dimension of the manifold. In particular, if N is compact, then N is diffeomorphic just to the torus. Okay, so how do we prove this? First of all, observe that since we are assuming that we have vector fields which are complete, independent, and commute, then their flows define a Lie group action and a Abelian Lie group action of Rn on the manifold. Sorry, this should be an N2. And this should be, well, Rn, the math BB. And, well, I don't know if it is clear why they define an action of Rn, or I should, well, basically the way we are defining the action is using the flows of the vector fields. These are the flows of each of the vector fields, and since the vector fields commute, their flows also commute. So I can write this way, but I could write it any other way, like phi tn xn composed with phi g2 x2 blah blah blah. Sorry. Okay, so this is how we define this action, and we can check that for a fixed X on the manifold, this mapping is an immersion. Sorry, 1 second. Hence, the image of this map which is called the orbit of the action, is an open set in N. But since N is connected, then this orbit must be the whole manifold. Sorry. Because if it were not, if it would not be the whole manifold, since it is open, then we would have two connected components, which would be a contradiction. Okay. Then we have this classical result that every orbit of an action is the quotient space of the group by the isotropy subgroup. And since this mapping is an immersion, it is a local diffeomorphism. So necessarily the isotropy subgroup must be discrete. And well, this is a detail that I will not prove, but one can show that this discrete subgroup is indeed a lattice set K for some K less or equal than N. And finally, using this and this, we conclude that the submanifold, the manifold is the quotient of Rn by the lattice, which is just the torus times Rn's. Okay. More questions or comments?
This time I will let you leave a little bit.
Thank you. Okay, well, this is the more involved part. Well, this part was a little bit involved too, but I skipped some details. But statement 4 is the most involved, but also the most interesting, at least from my point of view. So this is the existence of action angle coordinates, basically. Okay. So for simplicity, let me denote with capital F the function from M. Once again, this was the lemma for a general manifold. Now we are considering again our symplectic manifold with the integrals and so on. So let F denote the function from M to Rn, which is whose components are the integrals. And we can show that for each I in Rn, there exists a neighborhood D, such that the preimage by F of this neighborhood is diffeomorphic to D times the preimage of the point I. Y, sorry. Then, and in addition, the restriction of F to this set is a trivial bundle from D times the preimage of Y, or what is the same, the preimage of D modulo a diffeomorphism to D. This is a trivial bundle. Well, we will use this to construct a neighborhood of our submanifold M lambda, because we can write our submanifold M lambda as the preimage of some lambda on Rn, and then we can construct a neighborhood, in fact, what it is called a tubular neighborhood of M lambda on this way. Observe that, well, basically by construction, by construction and using this result, the integrals f1 to fn are coordinates on D, because, well, this is a trivial bundle. And on the other hand, we know that M lambda is diffeomorphic to a torus. So, well, we can consider coordinates on M lambda, which are angular coordinates of the torus. And I will call them these CI. In a future slide, I will explain a little bit better what how these angular coordinates are defined in relation with the lattice that defines the torus. Okay. In these coordinates, Ci, Fi, we could the symplectic form could be written as something like this in principle. But then we make some observations. First of all, M lambda is Lagrangian. So if we restrict omega to M lambda, it must vanish. Restricting to M lambda means that the functions Fj are constant. So we don't have this term, we don't have this term, we only have this term, so this must vanish. And well, I will skip the details because basically these are ugly computations, but one can show that these terms and these terms only depend on Fi. They do not depend on Ci. And thus, we have that our symplectic form can be written on this way. Well, now we use this notation. I will call this one form omega I and these two form beta. And well, as I said, these do not depend on psi, on the coordinate psi. Well, I'm using slightly of notation. We can identify this as a one form on D and this as a two form on D, because they only depend on the Fs, which, as I mentioned before, are coordinates on D. In addition, this is closed. So these one forms on D must also be closed. Well, but this is an open set of Rn, so they must be exact since they are closed. So we can write omega I as the differential of some function Si and beta as the differential of some one form gamma. We can also check that this one can show that these functions Si must be independent, functionally independent, and then we can use them as new coordinates on U. So we, instead of coordinates F, we will now use coordinates Si. And now we make a shift on the angular coordinates on this way. We just add some to is Ci, we add gamma I, where gamma I is the component of the one form gamma in terms of these new coordinates Si. Well, geometrically, basically what we are doing is changing the initial points of reference for angles in the torus. And well, finally, using these changes, we have obtained that omega can be written on this way. So these coordinates are Darboux coordinates. Now observe that the Hamiltonian vector field of Si is the partial with respect to phi. Well, basically this is because they are Darboux coordinates. So the partial of the Hamiltonian function with respect to phi is acting with this Hamiltonian vector field on H, but the Hamiltonian vector field of Si on H is the Poisson bracket of Si with H, but Si is a function of the Fi's, and we are assuming that Fi with H vanishes. And well, using the properties of the Poisson bracket, this Poisson bracket must also vanish as a consequence. And therefore, since this partial derivative vanishes, the Hamiltonian function is a function. Sorry, this should be an H. The Hamiltonian function depends only on the action coordinates. So therefore the Hamiltonian vector field can be written on this way. And we call the partial of the Hamiltonian function with respect to SI omega I, which these are the frequency functions and depend only on the action coordinates. And well, basically this completes the proof or the sketch of the proof, but well, let me mention a little bit an explicit expression for the action angle coordinates. This is interesting for knowing how are they constructed in the proof of the theorem, but it's not actually useful for obtaining them in practical examples. But well, in order to construct action angle coordinates in interesting examples, actually one uses Hamilton-Jacobi equation, as I will explain later. But well, in order to understand the proof a little better, let me mention this. So first, angle, how we construct angle variables. We have a point on an R submanifold M lambda, and consider the fixed points of the action on that point. That means solutions of this equation, where phi is the action of Rm on M defined by the flows of the Hamiltonian vector fields. We can show that this equation has a finite number discrete solutions, and so well these solutions form a basis of the lattice. And basically, using the implicit function theorem, we can see that the solutions of this equation will depend smoothly on X. Now we consider another point Y of M lambda, which is given by the action with parameters A on X, sorry. Then we define the angle coordinates on this way. Well, this 2 pi here is a matter of convention. You could not put the 2 pi and then take modulo 1, but whatever. And what about the action variables? Basically, fixing these basis of the lattice uniquely determines the set of basis cycles of the fundamental group of the terms. Well, I think this is well, more or less basic topology. So well, now let us consider a one form on some neighborhood, on some open set of the symplectic manifold, such that the symplectic manifold is the different on that open set is the differential of alpha. And to each torus, we assign this number 1 over 2 pi of the integral along the cycle of this one form. As once again, this 2 pi is a matter of convention.
Moment, yes, a second.
Yeah, of course.
Because in the coding, these integrals you have written is I1 by 2 pi. When you write this in coordinates, the alpha, sometimes you can write it like pi dqi. And the thing is that because you know they are related to the omega, and in quantum mechanics, in primitive quantum mechanics, this expression appeared for the quantization of certain systems. They appear that this integral must be some integer number, and they were used to work for certain integrals of motion. Well, integrals of motion, no, quantization rules for certain systems. But it is cool, yeah, because the integral about the gamma I that they are just cubes, can be written like the integral over a surface containing the gammas like the border of the omega force. And they can be understood geometrically, yeah?
Yeah, I don't know much about geometric quantization, but I know this kind of things about certain things on cycles being integers and so on are some topological constraints that you need for do some quantizations and so on, but well, I don't really know much about that. So
the thing is that for certain, if you want to know whether omega is exact or not, sometimes in quantization you have to check out whether there exists some potential whose differential is the omega. But this result does not happen to be always the case, and the way of checking it out whether it is true or not is by means of doing integrals of this sort. This kind of integral that appear in topology and to consider the topology of certain manifold. There are lots of theses, but I don't want to say more too much because without details is difficult to understand. But it's related to something to very interesting problem.
Yeah. Okay. Well, we can show that these functions Si up to a constant, they coincide with the action variables. By the way, let me comment that I have considered here the Liouville-Arnold theorem only for when M lambda is compact. This is how it appears on the book by Arnold, but it has been generalized for the non-compact case. The thing is that, well, the result essentially is the same in the non-compact case, only that instead of angular coordinates of the torus, you have also coordinates on Rn, like using this lemma I presented before. Instead of the torus, you have torus times Rn. The thing is that things that are topological properties that are automatically satisfied for compact manifolds, you have to impose them in the non-compact case, and things get more involved. But well, in the references, I have leaved a paper in which they prove the theorem for the non-compact case. Okay. So in order to understand better these action angle coordinates, I will present an easy example. Well, our favorite example, the harmonic oscillator. Well, to be more interesting, the n-dimensional harmonic oscillator. Consider the Hamiltonian system on R2n with the standard symplectic form and this Hamiltonian function. For simplicity, I had taken the mass and the frequencies to be equal to 1. And well, as it is well known, this is a completely integrable system. And indeed, we can check that these functions, which are essentially each of the components of this sum, are integrals. And well, they are functionally independent almost everywhere. Essentially, well, when pi and xi do not vanish simultaneously. And in this case, the diffeomorphism with the torus is pretty clear, because if we write the level set of these integrals, they are essentially circles, and well, we call that the torus is simply S1 times S1 n times. Okay. We can now write the Hamiltonian just as the sum of these integrals, fi, and we can define a new coordinates phi I as the arctangent of the quotient of xi by pi when pi does not vanish. And well, by
I have a remark.
of course,
That's not well defined.
yeah, you're completely right.
But the thing that that's the obvious thing. We can do it about minus pi to pi. But the fun thing is that the differential of phi I is well defined.
Mhm.
Okay, so even when the phi I you define can be defined, for example, for different values of pi or for certain intervals, yeah. The thing is that the differential can be defined globally. The trick is you can define phi I locally for certain intervals, okay, and then the differential on those intervals is defined, and you can see that these intervals can be overlapped in such a way that the differential of phi I on each interval what is defined coincides with the one that is defined another one, and this is because the arcotangent of this quotient. Okay, the main definition of cotangent is between minus pi pi half and minus pi half, but you can always add some constant to that, kp. You can change the domain of definition of the arcotangent. So doing so, you can define that globally. It's a technical detail, but sometimes it's important.
Yeah, you're right. Okay, thank you. Okay, so basically, these phi i's, fi's are action angle coordinates. Of course, in this really easy example, we have just constructed by observation, or for the Spanish speakers, for la cuenta de la vieja. But of course, this is not how you construct them for more involved examples. But well, that's why I will talk about the Hamilton-Jacobi theory later. Well, in this case, the Hamiltonian vector fields of the integrals take these expressions, and the Hamiltonian vector field of the Hamiltonian function is this one. So the fi's are constants of the motion, as we already knew, and the fi move. Well, the time derivatives are one, so they basically these are lines, straight lines. Okay, now let me talk about Hamilton-Jacobi theory. I will present the Hamilton-Jacobi theory in two ways. First, from the classical way, let's say, from canonical transformations. And then later I will talk about a more geometric approach to Hamilton-Jacobi theory. Yeah, I'm realizing that maybe I don't have much time, but well, maybe I will omit the geometric one because it's less related with the rest of the talk. Well, okay, so suppose that we have two sets of Darboux coordinates. For simplicity on R2N, but I think this would essentially work on a symplectic manifold too. Then this means that we can write the symplectic form either on this way or this other way, or what is the same as minus the differential of this one form or this other one form. Then on an open subset, the difference between these two one forms must be exact for some function on this subset. Now we assume that the Jacobian metrics of the coordinates capital Q, lowercase q with respect to the coordinates lowercase p and q is non-singular. And then we can express, well, this on some neighborhood, which is a subset of U. And then we can express this function f of q and p as a function s of the lowercase q and uppercase q. And this is called the generating function of the transformation qp lowercase to qp uppercase. Well, there are different generating functions depending on basically in terms of which coordinates you write this transformation. Like there are other generating function like for q and uppercase p and so on, but whatever. You can look this, for instance, in Arnold's book. Okay, then we have that the differential of s takes this expression, and therefore we can write the lowercase pi as the partials of s with respect to lowercase qi, and the uppercase pi's are minus the partials of s with respect to the uppercase qi's. Now, let us additionally assume that the canonical transformation is such that the Hamiltonian function in these new coordinates depends only on the pi's. Then Hamilton's equations take this form. But since pi's are constants of the motion, we can fix initial conditions and obtain that this is some constant E. And this equation, this partial differential equation, is known as the Hamilton-Jacobi equation. Okay. Now let me recall that we can obtain action coordinates as in terms of these integrals along cycles. So if we assume that our generating function is separable, that means that we can write it as the sum of functions with depend only on one of the lowercase q's. Then we can rewrite writing these pj's as the partials of s with respect to qj's. We can rewrite, we can obtain action angles on this way. Now we use these action coordinates as the new uppercase qi, let's say. So we also have a generating function for the transformation, for this new transformation, instead of qi pi to uppercase qi pi, we have the generating function of the transformation to this si and these phi i's that we want to find, that are the action coordinates. Then the angle coordinates, sorry, and the angle coordinates will be just minus the partials of this new generating function with respect to the action coordinates. Okay. This was maybe a little bit confusing, so let me illustrate it with an example. Well, the example I presented before, in fact. So in the case of the harmonic oscillator, the Hamilton-Jacobi equation has this expression, but we make the answer that the generating function is separable. That is, that can be written as sum of functions with depend only of x1 and one parameter e1 till xn with depends only on xn and en, where these are are such that they add to the total E, the total energy. Then we can reduce this Hamilton-Jacobi equation to a set of equations like this. And well, the solution of these equations are these ones, which, as Javi mentioned before, this actually is not well defined globally. Well, whatever. Then we can obtain action coordinates in terms of this integral, and we obtain that they are just a multiple of these energies EI. And well, we now write the generating function in terms of these new coordinates and derivating it. Sorry, this should be W. Derivating this new generating function with respect to the coordinates Si. We obtain the angle coordinates, which are for a multiplicative factor. They are the ones that we obtained before. Okay, I think I'm on time now, or so I don't know if you want me to continue or.
For me, it's okay, but the public can say what they want. I mean, maybe you can finish the Hamilton-Jacobi theory.
Yeah, I think I can sorry, finish this. I will skip the camp theory and mention the generalization, which are really brief. Okay, so basically the idea of the geometric approach to the Hamilton-Jacobi theory is considering well sorry, for this I will restrict for simplicity to the cotangent bundle. But there are also Hamilton-Jacobi theories for arbitrary bundles, but whatever. The basic idea is that we want to project our Hamiltonian vector field to a vector field on Q instead of the vector field on T star Q, and we want a section of this vector bundle which allows us to recover integral curves of this vector field from integral curves of this vector field. Well, basically this condition of related integral curves is the same as the gamma related condition, which is this condition, or the commutativity of this diagram. We additionally assume that this section, that is this one form on Q, is closed. Then making some computations, usually done in fiber coordinates of the cotangent bundle, we can show that this condition is equivalent to this other one. Now, since gamma we assume it is closed, locally is the differential of some function. And then we can, since at least locally, we can write this equation as this. But then we have that this is just the differential of a function on Q equal to 0. So locally this must be constant, and this is just the Hamilton-Jacobi equation, the classical one. And well, we have this theorem that if we have a closed one form, the following assertions are equivalent, that gamma maps integral curves of the projected vector field to integral curves of the Hamiltonian vector field. This equation, which is like a more geometric version of the Hamilton-Jacobi equation, or that the image of gamma is a Lagrangian submanifold of T star Q with the canonical symplectic form. Once again, we are seeing that everything is a Lagrangian submanifold. And well, this Lagrangian submanifold is invariant by the Hamiltonian vector field of H. Well, I will skip the proof. And we call a complete solution when it depends on a solution of the Hamilton-Jacobi problem is one form which is closed and satisfies the Hamilton-Jacobi equation, and we call it complete solution when it depends on n real parameters, and this map is a diffeomorphism. A local diffeomorphism, sorry, it doesn't need to be a global diffeomorphism.
Okay, yes, a comment about, well, maybe you can continue, I will tell afterwards.
Okay. And well, since we have this diffeomorphism, we can invert it and project onto, so basically the inverse of this diffeomorphism is a map from T star Q to Q times Rn. Then we can project into each of the components of Rn. Well, this is the projection I have written here. And these are functions from the cotangent bundle to R. And we can show that these functions are constants of the motion in involution. Well, once again, I will skip the proof. What did you wanted to say, Javi?
Indeed, that since the functions you define are constant of motions and in involution, and they define the particular solutions, a complex solution, when you gave at the very beginning, okay, every solution is given by several functions in involution, okay, that are constant. So that means that every particular solution, the complex solution, is a Lagrangian submanifold. So it is a foliation by Lagrangian submanifold. This is a complex solution. It's a way to define it geometrically, that a complex solution is a foliation by Lagrangian submanifold.
Yeah. See, yes, you're completely right. Yeah, in fact, they are more general definitions or more general notions both of Hamilton-Jacobi theory and of integrable systems. Well, they are essentially the same or very closely related. That, as you say, instead of using functions, they use just foliations. But as a first introduction, I prefer to use the version with functions.
Yeah, sure. The only thing is that as a corollary, let us say, you can give the general approach, but
Yeah, of course.
common. I mean, it's okay.
Okay. Well, just once again, we have the example of the harmonic oscillator, and well, just to mention that if you take the differential of the generating function I mentioned before, this is a complete solution where the parameters are the EIs. Taking its inverse and projecting it, we obtain the constants of the motion that we already knew. And well, the image of this complete solution are the Lagrangian tori that we already knew. Okay, well, I will not mention the theorem explicitly, but just for you to know, Kolmogorov Arnold Moser theory basically is combining Liouville Arnold theorem with perturbations. So it's studying how can we perturb a completely integrable system in such a way that it's still we have a diffeomorphism relating the invariant tori with some new tori. Very briefly and roughly, this is the idea. Okay. And just to conclude, as I said at the beginning, there have been studied a lot of notions of integrable systems in many contexts. So I will by no means be exhaustive, but I will just mention some generalizations. First of all, as I said, we have the Liouville-Arnold theorem for the non-compact case. As far as I know, this has been proven by Fiorani et al. I don't know if it has been proven by other people too. We also have Liouville-Arnold Nekoroshev theorem, which is for the so-called partially integrable system, which is essentially that we have less integrals in involution than degrees of freedom. So in this case, we obtain like we simplify our equations of motion, but not as much as if it were completely integrable. Then we also have non-abelian integrable systems, which is when these the Poisson brackets of the integrals do not vanish. Then it's called non-abelian because in this case the flows do not define an abelian action on the manifold. We could also consider integrable systems with singularities, which is points for which the rank of this function defined by the integrals is less than n. And well, these are some references, especially to highlight the book by Arnold and the original paper by Liouville. And that's all. Thanks for your attention.
So thank you very much, Asier. Is there any comment, remark?
I have a question.
Okay.
It's related to like this Liouville theorem.
Uh-huh.
Because I was reading recently this paper that was mentioned once, some comments about history theory and applications of simulating reduction.
Mhm.
And there was a quote, I would say, in fact, one cannot globally split off cyclic variables for S1 action on the configuration space of the heavy top. And later it says that it is related to Hopf vibration and how it is related to this theory, because it sounds like this is all connected.
Oof.
Well, I think I know the answer, okay?
Okay. I leave you the honor to answer for
I
me.
guess. You know, what's Asier has been described as has been the nice picture, the nice way of integrability. Yeah, the system that is integrable, it means that you have these functions in evolution and so on and so on and so on. The problem of that is that normally it does not work everywhere. It works at certain parts, and there are several points where this fails and things of the sort. So in the rigid body and other mechanical system, the behavior is mixed. Asier, can I show something?
Yeah, of course. I stop sharing screen or
Yeah, please.
yeah, 1 second.
This is reality.
Okay, yeah.
I mean, real Hamiltonian system looks like this. Wait. Do you see it?
Yes, we see it.
Oh, I mean, with integrable systems, the Torrey and the Liouville theorem works at parts, at the extent. You can see the Torrey in certain parts, yeah? But the behavior is mixed. So in certain mechanical systems, it does not work everywhere, and you have to look for more general things. I mean, I don't remember exactly how it was for the case you said now, but I think that the point is that this structure is not well defined everywhere. Indeed, the thing is, in the problem you said, there is a Hopf vibration, and the Hopf vibration does not fulfill things like this. Okay, a Hopf vibration is an S3 to S2 vibration, okay, that it's not trivial. And in that case, you can, well, the rigid body, truly speaking, it will be something like the cotangent to that, I guess, because it's a S3 normally. S3, the cotangent to S3, but more or less it's related to this. I can check it out exactly, okay? But the main idea is that what Asier did is just in general, a certain subsets of the system you are studying, yeah? But it's not the usual stuff. There are systems which are not there are systems that are integrable, as you said. There are systems that are a certain open subsets of the configuration manifold, the phase manifold, they are integrable. And there are systems which are even super integrable. They are in the stronger conditions. So every system is a case on its own, and it has to be described this way. But about the Weinstein paper about the story of the reduction, well, I can check that part exactly to see what they meant, but I think that it was something like that. Does this answer your question?
Yes. So the case is that system described there was not integrable, and
Yeah.
this whole story about tori fails.
Yeah, I mean, it's what I said, that there are systems that are integrable, there are systems that they are not integrable, and there are systems that they mix both behaviors. And as I said, there are even super integrable systems. Okay, so it's like a zoo with many possibilities, and it's well, here this is a foundation of mechanics. Okay, so here, as far as I remember, you should have wait. Okay, little things like this, you know, these are Poincare maps and things. They are okay, things of this sort. To say, this is well, when you have systems which mix integrable and integrable pictures, for example, this is a two-dimensional one. It happens that in parts where integrable, you have things like things that are diffeomorphic to circles, yeah, because T star R system, Tori, they are just cycles, things that they're diffeomorphic to cycles. So there are regions where you have these things, you have integrability, you have certain functions and involution, and they are well defined, and they are the level sets, they are compact, like here, and then you have things that, you know, these points. Here, there is no integrability at all, there are many problems, yeah? And so you have diagrams of this sort. This is the easiest thing. And here you have many examples in this work about that. And integrability, non-integrability is something that people are studying all the time with different systems or everything, as you said. Well, what I said is the general theory, the theory where everything works fine, it's wonderful, but reality is much harder than that. And it's closer to the things he said at the last, in the last slide. I mean, non-commutative integrability or partial integrability or things like that. So indeed, other things are rather about that. Indeed, there is just one thing I can show you also. I prepared, and this is a paper by action angle coordinates for integral system on Poisson manifolds. Okay, and here at the very end, for the standard Liouville theory, this is what Asier did. At the very,
Can you make it bigger, please?
so yeah,
Can you make it bigger?
yeah, yes, sir.
Oh, yeah, thank you.
Yeah, wait, because I was looking for it. Action angle for non-commutative integrable system on Poisson manifold. Poisson manifold is a generalization of symplectic one, but you see, functions are independent. Several functions are an involution with the function f1, fs, the sum of all the dimensions of the manifold, because you have a here. Well, this is the condition that you have given. So they are linear independent. Well, there are several conditions, standard Liouville theory for non-commutative integral system. You know, here your conditions are a little bit relaxed, and you see, you find things like the ones, as you said, yeah, Tori times R, and then certain manifolds B and minus R, yeah. These things are generalizations, and there are lots of things. This paper is very recent, something when it was written, 2008. And then in research is something like a couple of days ago, yeah. So you would have lots of things, and you can work and you do a lot of things about this stuff. There are lots of works out there. Many people involved in this. Álvaro Pelayo.
Yeah. I was going to mention that. Also related with these topics is the thing about momentum polytopes and these kind of things.
Yeah, well, San Diego, this is simply a classical integrable system. So, well, here you can. Wisterman. This guy is very famous. Many standard works about symplectic geometry and related topics are by him. Lagrangian and symplectic action, as always. And here there was, well, publications. Well, this is the Institute for Advanced Study in Princeton. The best place in the world you can finish. And here you have a list of many papers. And here there must be several of them concerning non-integrable, non-commutative integrability, because he was working. Well, it's a matter of taking a look at it. But also you can see that the journals, some of them, they are very, 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 very good. Negaciones Matemáticas, this is selective invariance and semi-torus systems, quantum systems and things like that. This is another remark. So you see, there are lots of things. Another remark, Hamilton theory is the limits, classical limit for a Schrödinger equation in...
You're completely right.
And there are some people that are trying to understand Hamilton Jacobi theory for quantum systems, but they are infinite dimensional, so it's hard stuff. And I think that that was everything I had in mind. Well, I could say many things, but they are not. I don't know if they are interested or not. So just ask what you think it can be interesting, and I take a look at whether I can be helpful. Thank you.
Okay, so are there any more questions or comments? No? Okay, so we will leave it here. Next week, we'll have a talk by Daniel Pérez Palau from International University of La Rioja about the three-body problem and things like this from a dynamical systems point of view. Less geometry, more dynamical systems next week. So see you all in a week.
Bye.
Good night.